Are you struggling at the game of pool? Well, pool is a difficult game. There's a steep learning curve when it comes to learning how to play the game of billiards. And without proper guidance from professionals or experienced friends, it can often lead to frustration or discouragement. CueTips is a computer vision based pool game, which acts as a personal coach that guides your shots with precision. Our goal is to create an immersive and responsive experience that is both precise and engaging. Our project has three different use case requirements. Firstly, we wanted to make sure that the distance between the predicted ball and the actual ball location was less than 0.2 inches. Next, the angle between the predicted trajectory shown on the table and the actual ball trajectory that the ball followed should be no more than 2 degrees. Lastly, the end-to-end latency from the time the table was detected to the time of projection should be less than 100 milliseconds. Here is what we achieved. We achieved a distance between the predicted ball and the actual ball to be 0.05 inches on average. The angle between the predicted trajectory and the actual ball trajectory was 1.13 degrees on average. And lastly, we managed to achieve an end-to-end latency of 22 milliseconds on average, which far exceeded our expectations. We will now go over the 6 different subsystems that our project has. Our first subsystem is a wall and pocket calibration system. This detects where the pool table walls as well as the 6 pockets are using canny edge detection and OpenCV's Hoff lines. These are calibrated and set in the beginning and kept constant while the software runs. Should there be a shift in the camera, all we have to do is rerun this calibration step. The green lines indicate the walls and the blue balls indicate the pockets. Our ball detection subsystem is responsible for detecting all balls currently on the pool table, excluding the ones already pocketed. In order to perform accurate ball detections, we first apply a green colored mask onto the table to filter out the table for accurate ball detections. We then apply a Gaussian blur onto the image and then use OpenCV's function Hoff circles to detect the balls. Using a white colored mask, our subsystem also differentiates between the cue ball and other balls. It is then stored as 2 separate attributes globally for the physics engine to access. Next, we have a cue stick detection subsystem, which finds the cue stick on the table and saves it as 2 coordinates, the first coordinate being the tip of the cue stick and the other being the back of the cue stick. This is also done using color masking by OpenCV and allowing us to differentiate the cue stick from the rest of the cue table. In this video, you can see the outline of the cue stick. Next is our physics engine. Our physics engine takes in data from all other subsystems and computes the predicted trajectory based on the user's aim. When the user holds the cue stick close to the cue ball, the physics engine detects this and calculates the shot to the nearest ball in real time. Our physics engine can also detect bank shots by taking into account reflections from the wall. It also detects when the ball enters the pocket, as shown in this video. We built a web application for users to have a more interactive experience and to look at the detections in software in real time. The front end of this application was built using React, and the back end to run the different subsystems and stream the video feed was using Flask. As you can see on the right side of the video, the user is able to verify the detections of their balls, pockets, walls, cue stick, as well as their predicted shot trajectories. On the left, the users can select where in the cue ball they intend to hit to add some spin. After the user has executed their shot successfully, our software will provide users with recommendations on whether they managed to execute their desired shot.
Okay, so here we have our table mount. This mounts both the camera and projector up top securely. We originally thought of building this ourselves, but realized it would cost a lot of time. So we kind of bought an out-of-the-box solution, which is pretty nice. And so here we also have the LED light strips. This helps our computer vision system. Before, the detection was pretty unstable, but with these lights, it's pretty consistent and stable now, so that's been really good. And up there, like I mentioned before, we have our camera, which takes the frame data from the pool table. And we also have a projector up there too. And that displays the predicted trajectories down on the pool tool itself.
This diagram shows the interplay between the different subsystems in our product. First, the user spin selection is fed through a web application and into our physics model. This data is stored in the physics model and will be used in shot calculations. While the user uses our system, our camera continuously captures frames, which are used by our object detection model to classify the cue stick, pool balls, and game environment. These objects are then passed into our physics model when they are used to calculate a trajectory prediction based on the cue stick's orientation. The points are then drawn on a canvas, and these frames are sent to the projector, which will display the trajectory lines onto the table for the user to see in real time. Once the user takes a shot, they'll be able to receive recommendations on their technique through our web applications.
In order to execute the shot, the user first selects their desired spin location. In this case, the user will select the center of the ball. After the user has selected their spin, the user will aim at the ball and wait for the projection line to appear. The user adjusts their aim until a perfect shot can be taken. Now the user takes a shot.
We encountered and overcame many challenges, but three of the most notable were cue stick detection, inconsistent ball detection, and calibration with balls and pockets. Cue stick detection was especially challenging because of the need to balance both sensitivity and stability. When the user shifted the stick slightly, we wanted to be able to detect this and update the trajectory. However, we also wanted the trajectory to be still when the user wasn't moving the stick. Inconsistent ball detection was another issue we had to overcome, both identifying the cue ball as well as accurately detecting all balls within the frame. We had to overcome lighting issues and improve stability of our detections. Lastly, wall and pocket calibration was a challenge. Oftentimes, noise in the image would lead to inaccurate wall detection, and sometimes pockets would be misclassified as pool balls. To tackle these issues, we used a mask to remove noise and isolate the walls, and we introduced size and position constraints to classify the pockets. This project taught us a lot of valuable lessons. On the technical side, we learned about the challenges involved in providing real-time feedback. There were many factors we had to consider in calculating the trajectories, and though it seemed impossible at the start, we always found solutions to tackle the obstacles that we faced. On the product management side, we learned that one of the most difficult parts was integrating the different subsystems of our product. Careful planning and coordination was the key to our success. Thanks for dropping by our product, and thanks for all the course staff for all their support throughout the semester.
3, 2, 1. Goodbye.
Bye. Thank you.